let's look at some examples of using the derivatives of the inverse trig functions. So to start out with, let's just find the derivative of this function, 2 times inverse sine of x over 3. So for the derivative of this function, well, this function, I guess first the constant multiple rule says we can just write down that constant multiple of 2 and then take the derivative of everything that's left. But the stuff that's left, this inverse sine, it has an inside and an outside, right? The outside part is inverse sine, and the inside part is x over 3. X over 3, maybe the best way to write that is 1/3 times x. So we need to use the chain rule here, and the chain rule says take the derivative of the outside function, which is the inverse sine function, right? So the derivative of this function is 1 over the square root of 1 plus whatever the input was squared, right? So we get 1 over the square root, 1 plus, and then we put the inside function into this, and the inside function is 1/3 x. All right, now we need to multiply by the derivative of the inside function, but that's just 1/3. So what we get is, I guess, 2/3 times 1 over square root 1 plus, maybe we should multiply this out. This is, let's see, 1/3 squared is 1/9, so 1/9 x squared. This might be an okay way to write it. If we really wanted to, we could multiply these two fractions, which I guess we should do, and then move this 3 inside the square root. To move the 3 inside the square root, we need to square it, so we get 9 times the stuff in the square root. And when we distribute that 9, I guess it gets a little bit nicer looking. So 2 over the square root of 9 plus x squared. All right, and we're done. For another example, let's, on the graph of x times inverse cosine of x, let's find the equation of the graph of the tangent line at x equals minus a half. So we don't really know what the graph of this function looks like, but we can find the equation of the tangent line even though we don't know what it looks like, right? We just need to find a point on the tangent line and the slope of the tangent line. To find a point on the tangent line, we know that it's going to be x comma y of x, and we want the tangent line at x equals minus a half, so let's plug in minus a half. Minus a half comma minus a half times inverse cosine of minus a half. So minus a half comma minus a half times, and then inverse cosine of minus a half, I think, is 2 pi over 3. So the 2's cancel, and our point is minus a half comma minus pi over 3. Okay? Now we need to find the slope of the line we're looking for, and that's going to be dy dx. So to take the derivative of this thing, we need to use the product rule because it's x times inverse cosine of x. So that is, let's see, derivative of the first part, x, is 1 times the second part with no derivative, so 1 times inverse cosine of x, plus the first part with no derivative, x, times the derivative of the second part. And derivative of inverse cosine is minus 1 over the square root 1 plus, minus x squared. All right. Of course, this is the derivative function. Since we want the slope of a tangent line at a particular place, at a certain x value, we have to plug that x value into this function. So we need to evaluate this function at minus a half. We get inverse cosine of minus a half plus minus a half times minus 1 over square root 1 minus minus a half squared is going to be minus a quarter. Okay, and then we should simplify this. Inverse cosine of minus a half is 2 pi over 3. And then minus and minus, those are plus. So plus. In this denominator, let's see, this is 1 over square root of 3 over 4. So this is going to be 2 over root 3. And then, so 1/2 times this thing, the 2's cancel. So 1 over root 3. All right, so that means now we have a point up here and a slope right there. So that means the equation of our line is y minus the y-coordinate, so y plus pi over 3, equals the slope, which is 2 pi over 3 plus 1 over root 3, times x minus the x-coordinate of the point, so x plus a half. And there's the equation of our line. We could multiply this out and put it into slope-intercept form, but I don't think we would really get anything out of the experience. So let's just leave it here. As a final example, suppose we have a camera on top of a 5-foot pole and it's tracking a mouse that's passing underneath. If the mouse moves at 2 feet per second and passes directly underneath the camera, how fast does the camera have to turn to track the mouse? So so what I have in mind here is camera's up here, right? It's 5 feet above the ground, and the mouse is traveling by like this at a rate of 2 feet per second. So if we just pick some spot to call x equals 0, say, then we can write x as a function of time, or the x position of the mouse as a function of time, right? We know that the mouse is moving at 2 feet per second, so we could say that x is 2t. Right? Okay. Here I'm sort of arbitrarily deciding that t equals 0 is when the mouse is directly underneath the camera. All right, so you can see that when the camera has to turn to keep watching the mouse, as the mouse moves, the camera has to pivot to keep tracking the mouse. And it's this angle that we need to figure out, or the rate of change of this angle. Right? So we'll call that angle theta. We want to know how fast the camera has to turn. That's the rate of change of theta. So we need to express theta as a function of t, and then find the derivative of theta with respect to t. That's what we need. So let me redraw this picture. So the mouse, at some later time, the mouse will have moved, so that, say, this is at time t. Okay, so at some time other than time equals 0, the mouse will be somewhere along the ground here, and the camera is going to pivot to look at the mouse. We have an angle theta here, and this distance here, that's x, and this distance, that's 5. So it looks like the tangent of theta is x over 5. Okay, well, first of all, we need to write things in terms of t, because we want rates of change with respect to t. And x as a function of t is just 2t. So we get tangent theta equals 2t over 5, or 2/5 t. But since we want to know the rate of change of theta, we should solve this for theta so that then we can differentiate it. So take inverse tangent on both sides. We get theta equals inverse tangent of 2/5 t. All right, now that we have an explicit formula for theta, now we're ready to differentiate. So we can calculate d theta dt. This is going to be in radians, so it will be in radians per second. Because remember, when you're doing calculus, trig functions only speak radians. They don't speak degrees. And that goes for inverse trig functions as well. Right, we need to find the derivative of this function. So it has an inside and an outside, right? The outside part is inverse tangent, and the inside part is this multiplication by 2/5 function. So we need to use the chain rule. Derivative of the outside part is, derivative of inverse tangent is 1 over 1 plus input squared. And we need to put 2/5 in here, our 2/5 t. And then multiply by the derivative of the inside, and the derivative of 2/5 t is just 2/5. So we get, let's see, 2 over 5 times 1 plus, and then 2/5 t squared, that's 4/25, I guess, times t squared. And then we could simplify this if we wanted to. Maybe it would be worth it to multiply the numerator and denominator by another factor of 5, because that gives us a 25, which then we can distribute. So we get 10 over 5 plus 4t squared. So that's the rate of change of the angle theta with respect to time.